Are you filming me?
Yeah.
All right, take a picture of the class. It's a swell-looking class. All right, okay. All right, now, you guys, I have a question for you. Okay, now what we're doing is we're talking about significant figures. Significant figures, they show how accurately a measurement has been made. Okay. Now, recently I was in the hospital and I had open heart surgery. Okay, and they had to knock me out. They had to put me under. How many of you guys have ever been put under? Okay, scan the crowd, scan the crowd. You guys have had anesthesia. Okay, back to me, back to me. That'd go. All right, did you know anesthesia is stuff that's really meant to paralyze you? It is, okay? And so it's really very, very poisonous. Why do anesthesiologists make so much money when all they do is just sit there and watch the whole surgery? It's because they have to watch your levels exactly, okay? Now, since I had open heart surgery, let me ask you this. Focus right here. Would I rather, if I was supposed to have 25 grams of anesthesia, okay guys, would I rather have 25 grams or 25.0 grams or 25.00 grams? Oh, they're all the same, somebody says. No, they're not, all right? Because in math, everything is pure and ethereal, and you know, it doesn't really mean much. In science, measurements mean everything. There is a big difference between 25, 25.0, and 25.00. Because remember, the last number of a measurement has been guessed on. That's exactly right. So, you remember that means if this is 25, don't yawn on the video. If this is okay. If this is 25 like that, that means this could really be 24 or 26. Well, you know what? If I was supposed to have exactly 25, if they gave me 24, what might happen in the middle of surgery? I might wake up in the middle when they had my chest wide open. That would be no good. What if they gave me 26 accidentally? That could...
You wouldn't wake up.
That would be asleep after surgery like as in death, okay? All right, so the amount is important. See, this right here, 25.0, that means that could really be 25.1, or it could be 24.9. And this one could be 25.01, or it could be 24.99. If it's important, which one of these do you want? The last one, okay? Because scientists know that measurements have to be made accurately, and how they're written up here, this is about significant figures. Okay, now, here are like the 6 tedious rules. This is particularly where you're going to want to listen to this video, okay? Because I'm not going to write the rules down for you. I'll look them up on a site and give them to you. I'm just going to show you examples, and then hopefully just by practicing this, you're going to get these down, okay? All right, so I call these the 6 tedious rules of significant figures. Now, if you look here, it's 1, 2, 3, 4, 5, 6. We have 6 examples, okay? All right, so now to begin with here, all non-zero numbers are significant. So this would be 3. See, we're identifying the numbers of significant figures. So 123 grams has 3 sig figs in it, okay? Now, what if I have a 0 between non-zero numbers? They count as being significant. So this would be 4, okay? So that's 4 right there, okay? All right, so any non-zero number is significant. If you have a 0 between non-zero numbers, it's also significant. All right, now watch this. What if we have really large numbers, though, that have lots of zeros at the end? The zeros are the pain of this, okay? So, now you guys, if we have zeros that are to the right of non-zero numbers, and they're to the left of a decimal, like this, left of a decimal, those are just placeholders. They only exist to show how large the number is, okay? So then that means that's 1, 2, 3, 4, and then those are placeholders. So this would be 4 sig figs. No, it would not, because these zeros just are there just to show how large the number is. They haven't been accurately measured. Now, that's a big number. What about a small number? A small number less than 1. See, if I have 0.0025, those zeros really don't mean anything. They just go to show how small the number is. It's not like you can't measure something that is not there, right? So these are just placeholders. So you watch if you see this. Zeros that are to the right of a decimal and that they're to the left of a non-zero number, those are not significant. They're just placeholders. So this would be 2. But now, watch this. Did you notice that these zeros are to the right and the left, and these zeros are to the right and left? What if we have zeros that are to the right and to the right? Okay, now watch this. If I have this 0 right here, that is to the right of a decimal, and it's to the right of non-zero numbers, then that number, that 0, actually was measured. It could have come out to 251, or maybe 249. It just happened to end up to hit a 0. So we have to have a rule that shows that that 0 is significant. It's been accurately measured. So zeros to the right of a decimal and to the right of a non-zero number count. So that's 3. Okay? Now, how about this? What is the distance to the sun? The distance to the sun from here to the sun is about 93 million miles. Okay? Now, how about this? Do I know it's exactly 93 million miles to the 1 mile place? I mean, do I know where the sun is exactly? The sun even undulates. It goes in and out. No, we don't know that. Do you think we know it to the 10 miles, within 10 miles? How about the hundreds? Probably not. How about the thousands? Probably not. Maybe we know within 10,000 miles exactly where the edge of the sun is. Maybe. So we have to have a way to show how is that 0 right there significant. Okay, so what we do is we put a bar over it, like that. That bar over that 0 now says that there's 1, 2, 3, 4. It just happened that that 0 is, significant. It's been measured, and we have to have a rule for that, so we put a bar over it. We can also put it in scientific notation. Okay, now listen. I just went through those rules with you. Let's do it again real quick. Okay, watch. Oh, we're going to pan over. Good. What good videography. All non-zero numbers are significant. Okay? All zeros between non-zero numbers are significant. All zeros to the right of a non-zero number to the left of a decimal are not significant. If the zeros are to the right of a decimal and to the left of a non-zero number, they're not significant. These guys are just placeholders. Zeros to the right and to the right are significant. So if they're to the right of a non-zero number and to the right of a decimal, they're significant. If I want to show this 0 as being significant, I'm going to put a line over it. Okay? Now, let's see if you can do some examples. Here's some examples. 169. How many sig figs are there? 3. 3. All right, that's good because all non-zero numbers are significant. How about this one? 1609. 4. Good, because see, that 0 counts because it's between non-zero numbers. Okay. Ooh, Abby, what's the next one? It is 1. That is exactly right. See, these zeros are just spacers. Hey, what's this next one? Is that 2? Is it 4? It's 2. Those are spacer zeros, or placeholders. What about that 0?
Oh, it's 2.
Is this 2? Is this 4? Is it 5? Is it 3? 3 is the right answer because, see, this 0 is to the right and to the right. See how those zeros are to the right and to the left? Okay? They're to the right. That means they count. Okay, now see this number. If I wanted to take this number and if I wanted to change this number into scientific notation, what I would do is I'd put this decimal place right there, but then I have to include all the sig figs. Okay? So the best way to show a number is its number of significant figures is just to put it in scientific notation. 9.300 times 10 to the 7th. See, this shows how large the number is. How many sig figs do you see there? 4 is right. See? Just like we showed over here. Okay? It's easier to write it like this. Now, in the high school, they might teach you about addition and subtraction, the rules for it. But I'm just going to teach you about multiplication and division because it's easier, and this is more something that you'll use. All right, so here are the rules for using significant figures. This is where it really comes in important, and you'll see the reason why it's so important to learn it right now. For multiplication and division, what you do is you round your answer to the least number of significant figures. Okay, now, you remember how I told you that when I go swimming, I sink in the swimming pool, okay? Because I'm just a big sinker. Okay, I'm real dense, and it's a lot of work to swim. Okay, the density of something is the mass of something divided by volume. It's, in other words, in your volume, how much mass do you have? That's your density. Okay? All right, so now, pretty soon we're going to be doing these density measurements, and you're going to make this cool thing called a density column. And you're going to find the density of molasses and alcohol and water and glycerin, and then you're going to stack them, and it'll be really cool. Suppose I had you find the density of something, and you measured the mass of it to be 25.00 grams, and the volume to be 73.2 cubic centimeters. Okay? So, if you divide this by this, it's going to come out to this 0.34153000546 grams per cubic centimeter. Okay? All right, now, you guys, about this, you might want to say, Mr. Hawley, I'm just going to really show you how smart I am. I'm going to put that whole number down. Okay? Well, I'm going to tell you right now that that's a bad idea. Because, see, what you're doing is you're saying, you know the density of something to the tenths place, the hundredths place, the thousandths place, the 10,000ths place, the 100,000ths place, the millionths, the 10 millionths, the 100 millionths, the billions, the 10 billionths place. There is nobody even in NASA that can tell you the density of something to the 10 billionths place. All right? You can't do it. So what this rule says is that you round your answer to the least number of sig figs. Okay, so right here, how many is 25.00? How many is in there?
2.
Is there 2 or is there 4?
4.
Are those zeros to the right and to the right?
Yeah.
Okay, they're to the right of the decimal and to the right of a non-zero number. So see right here? Those count, don't they? Okay?
What does that say?
Say what now?
Wait, GLC.
Grams per cubic centimeter. So this would be 4. Okay, and 73.2. How many is in that? 3. That's exactly right. Okay, now everybody, round your answer to the least number of sig figs. What's less? What's least? 4 or 3? 3. So I can only have 3 in my answer. Okay? So right here, it's going to be 0.3. That's 1. 4. That's 2. Okay, is it going to be a 1? What does that 5 do to the 1?
Rounds it up.
It rounds it up. So the answer would be 2. All right, now look. This is an answer that a middle schooler using a balance and a meter stick in this classroom can actually get. Okay? You cannot get to the billionth of a gram per cubic centimeter because nobody can. All right? Thank you for watching this video.